Everyone, thank you for joining. My name is Miro, and today we'll be covering GPU accelerated HPO in the AWS SageMaker cloud. Let me go ahead and get my screen sharing going for you guys. All right. Let me know if you can see that. I can also change my resolution to make it less wide if that's annoying for you folks. Is it okay, Lena? I'm just asking, is the screen resolution and everything looking okay for you guys?
I'll make you as a co-host. Yeah, can you try now?
Yeah, I think it. Can you see the screen?
Yes.
Okay, great. All right, let's get going here. So to start out, I thought I'd do a quick intro to RAPIDS, which is a platform that's open source and has been in development for about 2 years and has a lot of NVIDIA engineers helping out as well as other folks in the community. And the goal of RAPIDS is to bring GPU acceleration to the popular data science tools that people use, primarily in the Pythonic world initially, things like pandas and scikit-learn that hopefully you're familiar with. But also more recently, I've been focusing on Spark and Hadoop and the Java side of the house. So to start out, let's talk a little bit about why we decided to build Rapids. Essentially because GPUs have very strong scaling. And if we expose our high-level code to them in a relatively seamless way, we can get tremendous benefits from the inherent parallelism that's there in many of our algorithms. And so because GPUs provide this hardware which exposes many workers, if we're able to do this in a way that stays out of the way of the developer, then everybody wins. And so the Rapids effort has been focusing on leveraging the underlying strength of the hardware, and then trying to accelerate data science in different dimensions where we have these sort of sub packages, if you will, things like cuDF for data frames, so CUDA data frame, cuDF, where you might be doing ETL and ingestion, cuML for CUDA machine learning, where you might be doing things like decision tree learning, dimensionality reduction, etc. Graph algorithms with cuGraph, and then we also offer zero copy transitions to things like PyTorch, TensorFlow, MXNet with DLPack, as well as other members of our ecosystem. So the idea is to leverage a very popular sort of memory representation developed initially by Apache Arrow and use that same representation to make sure that as data arrives on the GPU, it never has to leave. And it can be handed off between various libraries and everything stays fast. So as a result of all of this, if you look at sort of the historic evolution of data processing, we started out with things like Hadoop, where we were going as fast as we could on distributed computing platforms that were predominantly very inexpensive and could scale horizontally, and we were able to get significant improvement, almost 2 orders of magnitude, by moving to in-memory processing with Spark, and then taking that and refactoring it to work on GPU was something that was non-trivial and something that typically only experts could do, but that would get you another 10x on top of the Spark performance. The goal now, again, is to take all of these applications that are communicating on the GPU and CPU and make it so that the data only has to come in once onto the GPU from the CPU and will stay there and continue to be processed. So a lot of these copies and converts that typically used to happen at every stage of the pipeline are gone. And again, this is leveraging Apache Arrow under the hood to make everything interoperable so that I can hand you an object that I was just working on and you understand exactly how to pick it up and keep going. And so with that optimization, as well as a lot of other, software engineering goodness, we're able to take even something that experts used to have to spend a lot of time on and get another factor of improvement over that. So now with Rapids, we're looking at another significant, benchmark in the evolution of performance. So everything stays on the GPU, everything's very fast, and hopefully I'll convince you of that here with some demos in just a moment. If you're curious, you can always jump in on our docs page, as well as GitHub, and check out the latest and greatest. This is an ever-evolving project. Here is just a benchmark from TPCXBB, which is a data science benchmark, very popular in the finance community, where there's 30 different queries that we sort of competed to accelerate, and won by a very large margin. Again, just mostly because there's so much inherent parallelism that's available in modern algorithms that if we just spend a little time to make the libraries capable of tapping into that, we're getting something like 37x on average for the 1K benchmarks and about 20x speed up for the 10K benchmarks. One interesting thing that we'll also see in the cloud is that in addition to being faster when running on GPUs, it's also cheaper, which may sometimes be counterintuitive, because this is specialized hardware. And the reason for that is that, especially if you're renting, the amount of time spent on this is so short that you can have, tremendous power, but then be done with it and move on to the next workload, or hand it off to someone else to use. So this hopefully will feel approachable. And if you guys have any questions, either on the acceleration side or the TCO and cost side, definitely feel free to reach out during the talk and or after. So let me pause there for a moment to see if folks have high-level questions about Rapids. While I do that, I'll also jump into our Rapids documentation page. So if you ever go to, first of all, let's go to rapids.ai. This is the landing page for Rapids, and it has links to our blog posts. It also has a way for you to get started. If you want to learn more, it gives you a heads up for some of the prerequisites. And then it has a great tool, if you'd like to install in some particular way. So for example, if you want to install with conda or with a container, if you want to pick the current stable version or the most recently freshly baked nightly, you can click around in here. You want to get all the packages, let's say for Ubuntu 18.04 with Python 3.8 and the latest CUDA drivers. This presents you with a copy and pastable conda install command, for example, if you were to go the conda way. So this is a great way to get started. And there's many different ways, as I'll show you here shortly, to get started in the cloud as well. So the next bit is going to be to actually jump in and create a SageMaker notebook that we'll be using to actually run a Rapids demo. And we'll do that in two different ways. The first way will be to rent sort of a very cheap instance, which is fairly classic for SageMaker, in which we just will launch the work from there. And then once you guys see that end-to-end workflow, we'll switch into renting a slightly more expensive GPU instance as our notebook instance, which will allow us to do dynamic development. But without further ado, I'm going to go ahead and switch gears now and kind of give you a quick heads up about the HPO work that we're going to be doing today. Before I get into this, let me quickly take a 9-second pause to see if there's any questions or anything in the chat. Okay, no questions. Does anyone have any questions for me? I'll pause for just a moment. Okay, great. I'll take that as a no. Okay, so for the next phase of the workshop, we're going to be sort of setting up a combination of RAPIDS and SageMaker together. So I kind of introduced RAPIDS already. SageMaker is AWS's machine learning platform, which allows us to stay in a notebook environment and use familiar high-level Pythonic APIs to orchestrate potentially mountains of compute. It's really powerful and really great and really convenient, and it keeps improving. So I highly encourage you to dive in. What we're going to be doing today is taking a machine learning workflow that we've already built, and we'll containerize it or do what's known as building a SageMaker estimator. And we'll tell SageMaker what sort of parameters we would like it to explore of the model that we're hoping to improve. And then we'll ship that container and the search space to SageMaker and allow it to conduct experiments in parallel to figure out what model configuration produces the best results for us on the workflow that we provided and the data set that we handed it. In this particular case, we're going to be doing using a public data set. This is a data set coming from the Bureau of Transportation that has kept logs on flights for, since I think like the 80s. And so there's about 6 or 7 million flights per year from the domestic US carriers. And so you can query, multiple years of this data and get, let me jump onto the next slide here, and get all of the flight statistics. And we're going to be training a classifier model to predict whether or not a flight is going to be more than 15 minutes late to arrive. So essentially, we're going to take one of the columns that already exists in this data set, and we're going to treat it as our target for our prediction. Essentially, there's a column in there called arrival delay 15, which is a binary variable saying whether or not the flight was more than 15 minutes late. We're going to use that as our target or our Y variable, and then we're going to use all of the other features as our X or training features. And we're going to ask, in this particular case, a decision forest, either the training data and build a model that can predict whether or not a flight's going to be late on the unseen test data. And so we'll build this workflow, and we won't go into the details initially. We'll do that in the second section. So for now, just kind of assume that you have some kind of minimal ETL. In our case, all that we're doing here is we're ingesting the data from, in this place, Parquet compressed representation of columnar data. We're just dropping any samples that have missing values. And then we're splitting the data set into a train and test set. And that's all we're doing for our ETL. Very straightforward, no feature engineering, just a minimal amount of processing. In our training step, we're training either XGBoost or a random forest model. And then lastly, we're doing inference or prediction to figure out what our accuracy is as our metric. And so in the course of developing this work, we provided several different code flavors, either pandas and scikit-learn, which is kind of the classic data science open source stack, which primarily runs on a single thread of the CPU with the exception of the training step. We also have that same code, but now augmented with Dask, which is a parallelization toolkit, which allows us to get parallelization happening not just in the model training, but also potentially in the ETL and anywhere else. So this is kind of like enhanced CPU, if you will, or multi-CPU. And then we have the RAPIDS version, which is single GPU, which runs the parallel code to the pandas in the form of CUDA data frames, and then scikit-learn in the form of CUDA machine learning. And so this is, quite accelerated already, but we also offer, the addition of Dask with these libraries that exposes us to multiple workers, so that if we have multiple GPUs within a node, we can leverage them as well. So these are the 4 different code variants that are available that you'll see in your notebook. And with them, we'll be able to run and compare performance. So let's go ahead, and I'm going to skip over this estimator, sort of the creation of this container, and very briefly mention again that once we have our workflow containerized, all we do is we hand it off to SageMaker, and behind the scenes, it launches our container, spins up instances, replicates the data onto all of those instances, and then runs each of them with different hyperparameters being things like, the size of the decision forest, or the depth of the trees, or the learning rate, or any other parameter that's typically not changing over the course of the model fitting process, but is usually hand tuned by a data scientist. These parameters make great candidates for hyperparameter optimization. So assuming that we have that set up, SageMaker will do the rest for us and come back and give us the best performing model. So let's go ahead and get started, because it's going to take a little bit to spin up our notebook instance. So if you don't mind, I'm going to switch over, and I'm going to have 2 tabs here, one with the SageMaker. So let me see if I can get that going. 1 moment here. So if you go to AWS Management Console, and you can just search for SageMaker here and click on that, or you can scroll down and it's the first item in the machine learning section. So if you go into SageMaker, you should see a screen that looks sort of like this. Navigate over to the notebook instances, and then go ahead and click on Create Notebook Instance. So for the first version of this, we'll use the defaults primarily. So this is a T2 medium instance, which is a very lightweight CPU node, which is a perfect candidate for just being our development and notebook hosting environment. I believe it costs 4 cents per minute. So it's something that you can kind of even leave running and not feel too bad about. So let's call this T2 HPO. And then for elastic inference, we can leave this to none. For additional configuration, we'll leave this to none for now. We'll come back to this lifecycle configuration in the final step of the demo. The one thing that I encourage you to do is in the IAM role, this is like where you set permissions for SageMaker. Go ahead and click on create a new one, which will make sure that you don't end up having any conflicts with any previous IAM roles that you may or may not have created. So go ahead and in my case, I can't do that because I'm using a Rapids engineer account. So, but in your case, you should be allowed to click on create a new role. And then the only step that's in here that's a little tricky, or not tricky, but I guess custom, is that we're going to be cloning a repository. So if you go down to the Git repositories, there should be a dropdown that says clone a public Git repository to this notebook instance only. And the Git repository URL, I'm going to paste it in the chat. It should be github.com/Miro Enev. .ml examples. So let me put this in the chat. Let's see, is this actually the chat? I don't think so. Lena, where is the chat for this? Oh, Lena may not be here. Okay, I'm just gonna make this big for you guys. Hopefully you'll be able to see it and copy this. I think the only tricky part is my name, which is Miro Enev in the middle. This is github.com, Miro Enev cloud-ml-examples. All right, I'm gonna go ahead and click on create notebook instance here in just about 5 seconds. Again, please feel free to jump in and interrupt. Let's see more. Oh, chat, here we go. There we go. Okay, perfect. Thank you, appreciate that. All right, hopefully that's in the chat for you guys now. Can someone give me a thumbs up that they're following? I just want to make sure I'm coming through clearly for you guys. And chat thumbs up is okay too. All right, sounds good. So great. So I'm going to click on create notebook instance here, and this will start the launch process, which will take you probably about, let's say, 3 to 5 minutes, since SageMaker is having to spin up a whole new instance for you. I'm going to go ahead and open up one that I already have running, but you guys should see this pending here for a bit. Once it's ready, it will have these options that come alive. And once they do, click on the Open Jupyter tab here. Okay, great. So let's see, is this the one that it just kicked me to? Oh, this is the previous one that I was running, right? So one interesting thing, I guess, also worth mentioning is that this work was included in the official SageMaker examples repository. So one thing you could also do, instead of cloning that repository I just gave you, is you could click on this little brain icon on the left-hand side once your notebook is fully done spinning. And from it, you'll see all of these great SageMaker example notebooks. So if you click on view in GitHub, it'll probably take us here. This is a 4.4 K starred repo that has lots of examples and lots of different things. If you're curious to learn about SageMaker, this is a great place to start. Inside of hyperparameter tuning lives RAPIDS bring your own branch, which is where our demo lives also. Because of that, it's possible for us to replicate this directly into the notebook just using the UI. The reason why I asked you guys to clone the repo that you did was because it's a slightly fresher set of code that will allow us to do some additional features for the second part of the workshop. And in the very near future, it should make it into the official examples as well. So if you're curious to replicate it from the examples, you click on this little brain icon and you would scroll down into the hyperparameter section, which is here. And then eventually you would click on this. And so it shows you like a read-only preview of the notebook when you do that eventually. And then, whoop, not in this particular case, you would just click create a copy. I think this is because of my somewhat obscure VPN settings because we're using a team account. But you should be able to see a preview of the notebook, and you just click create a copy, and it will essentially replicate this in your local directory. But since we already cloned that directory, you don't have to worry about that for now. So I'll briefly walk you through the structure of the notebook, and then maybe take a few minutes to let you guys explore. I hope that your instances are starting to spin up so that you can follow along on your own screen. But for the most part, these are the things we already talked about. So we're going to be using the flight delay, workflow. We're going to be containerizing it, publishing it, and then using SageMaker Python API to do all the work for us. So let's go ahead and clear our kernel. And actually, was this one still running data? Oh, I think it might have still been. Oh yeah, so this is one that just finished running. So maybe I'll keep it without clearing it so you guys can see an example workload that's still in flight. So essentially what we're doing here is we're just coming in and starting out by making some key choices for the configuration settings. You can kind of skip this preamble. This is just making sure that we have an account and we are in a good region. Actually, the regions should either be US West or US East 2, or US East 1 or US West 2, sorry. Either of those regions is fine. If you're in a different region than that, you may want to change just because our S3 bucket of the data set that you're going to be replicating is in those two regions. And if you are running your compute in a different region from that, SageMaker will yell at you and not let you make progress. So one of the assumptions that SageMaker makes is that your data set and your compute are co-located, or at least within a region. So for the purposes of this demo, you should either be in US East 1 or US West 2. If that is a problem for anyone, please let me know. The way to change your region is if you go into the AWS management console and you navigate to the top right, you'll notice here there's a region selector. So US East 1 or US West 2. So North Virginia or Oregon are the ones that we have support for in this demo. They're both regions with relatively high numbers of GPUs, so you shouldn't have any issues renting. But if you do have any trouble, definitely please let us know. So, initially we just configure our SageMaker execution role and make sure our account and region are accessible. And next, we're going to be making some choices. This is where you can sort of configure how large or small you want your hyperparameter optimization to be. In the case of something that's a small hyperparameter optimization, you might run the 1-year data set with about 6 million flights, and you might run 3 cross-validation folds, which are kind of a data science-y term for improving the robustness of your result by shuffling the training and test data multiple times. You might run 10 experiments total, and you might run those 2 at a time. So this is what you might consider a small hyperparameter optimization, where you're only sampling 10 different model configurations and looking for the best one inside of those. A large hyperparameter optimization, on the other hand, might look at 10 years of data instead of just a single year. It might use more cross-validation folds for this data set, because now it's starting to become really large. You would want to bring in an instance type that has access to multiple GPUs so that you can distribute the workload across their memories and leverage them in parallel. And you might run 100 of these experiments, and you might run them 10 at a time. So this now is sort of serious business. This is what you might do before deploying to production, let's say, and this is something that's going to yield some confidence that whatever result you found is likely to be very good. So for the demo, we're going to be closer to the small HPO side. When we ran experiments like this large HPO using the CPU and GPU comparison, and we were finding things like, a 12x speed up in wall clock time. So the GPU finished in about 6 hours for those 100 jobs, whereas like on the CPU side, it was taking more than 3 days. And then about a 4.5x reduction in cost. Again, this reduction in cost is maybe a little bit counterintuitive at first, but it's very consistent with what our customers are seeing and we're seeing, just because of the way that GPUs are able to finish their work so much faster, and because of the cloud economics. AWS has these great EC2 spot instances, which I'm not sure if you're familiar with, but essentially they are a way to rent for up to 90% savings. In practice, I think we see about 70% savings. And so the trade-off for this cost reduction is that you could potentially get kicked off of your instance, but in practice, we see that out of 100 jobs, maybe one will get preempted. So it's really an awesome option is to use these spot instances. And I'll show you that in just a second. So, at a high level, again, we're going to be targeting ourselves mostly towards the smaller hyperparameter settings, but feel free to change them in here. The data set that we're storage type, and it's coming from the 2019 data. We offer options for, of course, larger versions of this data set, so 3-year or 10-year with more flights. And we also include the NYC taxi data set as something that you can plug in using CSV data, which is not compressed, but maybe more familiar to some folks. And just to show you what it would look like to plug in your own data set, if you're curious, you can jump into that as well. So next, we essentially tell SageMaker where our data source is going to be. And this is that public S3 bucket that we provide for you. And then we also tell it where we want it to place the outputs of the trained models. And in this case, we're asking it to just place those into the default bucket, which is built for you when you log in, and it's some combination of the word SageMaker, your account region, and your account ID. You can swap these around. You can plug in your own bucket if you'd like, and as long as your data set, is Parquet or CSV, and you can describe the columns of it, which we can show you in the second part of the workshop. You can plug in your own data set into here as well. So once the data set is out of the way, the next choice we make is whether we want to run with XGBoost or Random Forest. Here, we're going to leave it to XGBoost, which is one of the best performing non-deep learning algorithms out there. It's based on decision trees that are constructed in a sequence such that each new tree tries to fix the mistakes of its predecessors, if you will. And it's an algorithm that performs, exceedingly well. It's often in the winner circle in the machine learning marketplace and competition website Kaggle. So if you're looking for, a machine learning algorithm to try on a new data set, especially if it's a structured tabular data set like this airline data or the NYC taxi data, then certainly XGBoost is your friend. So we'll leave that there. We're going to do just 3 cross-validation folds, which, as I mentioned before, are the reshuffles of the training and test data that allow us to make sure that we're not just getting a lucky or unlucky sort of set of coin flips for when we're picking what the model sees during training versus what it gets tested on. So this just kind of improves the robustness of our result. So when we're evaluating our model, we'll provide the average across these reshuffles as opposed to just a single run. And here, we can pick which variation of the code we'd like to run. For now, we're going to pick the rapid single GPU version, which is kind of like the accelerated, the first form of acceleration before we start bringing in Dask. And if you're curious about these other code flavors, they should all be available in this code workflow directory if you want to jump into them. We're going to be doing a slightly deeper dive on that in the second session, or the second part of the session. So pick single GPU for our workflow choice. Here we can pick our hyperparameter ranges. Essentially, when we're doing optimization over these models, these are the parameters that determine the learning configuration. So how deep do we want our trees to be? How many trees do we want in our decision forest? And what percentage of features do we want to be used at every point when a branching decision is being made inside of the tree? There's many more parameters and ranges you can plug into here. This is just a starting set. If you have more ideas for this, you're welcome to add them in here. As you can see, all you have to do is just create a new entry in this dictionary where this is a keyword that's recognized by the machine learning algorithm under the hood. And then you have to sort of tell SageMaker what kind of a parameter. Is it an integer? Is it a continuous parameter? Et cetera, et cetera. So the last few choices that we have are, how do we want to search the space of hyperparameters? Do we want to use a random strategy that just picks places and then evaluates them, and then when it's making a choice for where to look next, it completely is disconnected from past decisions because it's random? Or do we want to use a Bayesian strategy that looks at the past outcomes and tries to do a form of regression to figure out where to go next? For the purposes of this demo, we have selected random. You're welcome to plug in Bayesian. I think they're thinking about adding additional search strategies in here. But again, it's up to you. I think both are fine. If you are searching over really large hyperparameter sets, random is a really powerful, surprisingly powerful tool to make progress with just a few hyperparameter settings like this, and only running 2 experiments in parallel like we're about to. Bayesian is also a fine choice. So I think only 2 more configuration settings left, and then we're off to the races. So next we sort of make that commitment about how large our experimental sets are going to be. So here we say we want to run 10 total experiments or 10 total jobs. Each of these is going to be a instance launch with our code in a container on a new instance with their data set attached, running some HPO configuration within this range. So here we're saying let's run 10 of these experiments. Again, this is on the small HPO side. And then this is saying I want to be able to run up to 2 of those in parallel. This number is somewhat low on purpose, partly to sort of keep costs down for folks who are just getting started, but also because you may have to request a instance limit increase for GPUs in your region. Oftentimes Amazon will kind of be hesitant to give you their more powerful compute instances until you can figure out, they can figure out that you're serious. So there's this quota limit increase that you can, request for whatever region you happen to be in if you'd like this to go with more experiments at the same time. Typically, it takes about a day to get back a response, and you don't have to be very verbose. You can just say, I'm running this for research or for work, and as long as they can tell that you're a real human and you haven't been super delinquent in previous payments or something like this, they will give you access to GPU instances or any other kind of instances that you may have a quota limit on. But 2 is typically a safe number where you're below that threshold for having to request something. If you were, again, to do this at a higher level, you might want to have access to 10 instances at once and run this for 100 jobs. Okay, so let's keep going here. So this is just another setting that would cut off any jobs that end up running for more than 24 hours. This is more of a safety limit in case we have some kind of a bug in our code, but also because sometimes the CPU configurations, the CPU is not really great at doing very deep and wide forests. So we've definitely seen more than 24-hour jobs, and we kind of don't want those to run forever. So we'll terminate anything that's more than 60 times 24 seconds, or basically 24 hours. Okay, last choice, our compute platform. This is the instance type that we're going to be running on. And we have a little helper function that takes your previous choices and recommends a instance type to run on. You're of course welcome to just pick a instance type yourself, like directly with a string here. But the recommend instance type provides you with an option that's guaranteed to work on the configuration choices you've made so far, or at least one that we've tested. So in this case, because we picked the 1-year data set, it's saying, let's go with the P3 2x large, which is a single GPU. This is a single Volta 100 GPU with 16 gigs of GPU memory and 61 gigs of CPU memory. So, this is a fine choice for the single CPU version of this. And then lastly, the spot instances. As I was mentioning before, highly encourage you to check these out. These are typically producing, 70% savings on the GPU runs. I can actually show you here. Let me see if I can find one. Blah, blah, blah. Yeah, so here's a run that just finished, and because it was running with spot savings enabled, we got 70% savings on this from these training and billable seconds. So this is really awesome. Highly encourage you to do the spot instance training. All right, so that's all of our key choices that we just made. They're summarized here. So here's our input bucket, our output bucket, our compute choice, single GPU, our algorithm XGBoost with 3 cross-validation folds, our instance type, single V100 to P3 2x large. Are we using spot instances? Yes. What's our HPO search strategy? Random. How many experiments are we running? 10. How many at a time? 2. And then what's the maximum duration of any experiment? 1 day. So we have all of our choices, and now we're ready to actually, put them into play. So this workflow bit, again, we're going to come back to this in a little bit. For now, just assume that we have a working Python code that does this, that works with our data set. And if you're curious to dig into that code, there's the 4 different flavors: the multi-CPU, multi-GPU, single CPU, single GPU. I'll show you those in a bit. But let's just assume that we have that code. We can now, step into the part where we're kind of making it processable or digestible by SageMaker. So essentially what we're doing is we're writing a Docker file, which is kind of a recipe for how our software is going to be packaged. We're building this first layer on top of a RAPIDS image that we publish to multiple locations, including Docker Hub. And then on top of that, we install SageMaker training, which is something that the folks at AWS maintain, and it allows you to essentially just get a little bit of extra plumbing in your container that makes it easier for you to talk to SageMaker and figure out how everything is hooked up. And then lastly, we basically copy all of our custom workflow code, the stuff like the ETL, the training and the scoring logic into that container, and we call it done. We build this, we tag it, and then we push it up to the Amazon cloud, to their Elastic Container Registry. So that's what's happening in these steps down here. We're using the RAPIDS AI container as our base. We're adding in some environment variables that tell SageMaker what choices we just made above, so that when the container runs, it actually knows that we want it to use, for example, XGBoost. It knows how many cross-validation folds to run, and it knows that it should be running in single GPU mode. So with these environment choices sort of represented in our Docker file, we just augment it with a few lines to allow it to build some tools. Specifically, those tools are the SageMaker training stuff that I just mentioned, which helps us with that extra plumbing. And then we also add in Flask, which is just a server that we'll be using in order to be able to deploy our trained model so that we can send it inferences. And the rest of it is very straightforward. We're copying our local code with our logic, and that's pretty much it. We're just telling it that the entry point is executable, and that the thing to do is to run this entry point code once you land in the container. Here is the full Docker file if you're curious. So again, starting from the RAPIDS base image, we're setting the choices that we made as environment variables. We're adding in a little bit of software. We're copying our custom workflow, and that's it. So next we do a Docker pull of our base layer, just so that we have it locally, and then we build on top of that base layer everything that we just saw. So this takes about, in our case, took about 2 seconds, just because I think I've run this before, but typically it should take you about 45 seconds. This Docker pull of the RAPIDS-based container image might take you a little while. It might take you like 3 or 4 minutes because you're pulling maybe a significant, container base layer from the RAPIDS Docker Hub. So if you're following along and you're on this step, this might take you just a few minutes. The Docker build is quite fast. Next, we sort of create a Elastic Cloud registry where we're going to be publishing our container so that SageMaker can get access to it. So far, the container is just local to the notebook until we do this Docker push. And so now, after this push, it's being sent up to ECR. It may take another few minutes. So this is another point where you may have to wait just a little bit. But once that's ready, you should be actually able to get to more fun stuff, which is we can now take all of the stuff that we've built, all of our choices, and the container that we finally published, and we can package it into a SageMaker API that will allow us to run hyperparameter optimization. And so the SageMaker estimator API is our target. And so a SageMaker estimator is a fancy way of saying container with some logic. And the parameters that we're passing into here is just this dictionary. And so this image name is the name of our tagged container that we just built. So this estimator is going to be running our container. It has access to spot instances if you told it to. It's going to be running for a maximum duration of 24 hours like we told it to. It knows about where to place its model artifacts when it runs based off of the bucket that we told it to write to. And it has our SageMaker session and role. And so essentially at this point, we have taken our workflow and our choices and produced a SageMaker estimator, which is again what we need in order to make progress here. And so in this next step, we summarize our choices to make sure everything is consistent. And then we just test to make sure that our estimator is working correctly. So here's just sort of a sanity check. This is not running full-fledged HPO. This is a single experiment, if you will. And so this is just using the same estimator that we just finished and now running it using SageMaker. So you can see it started the training job, it launched the instance. Because we're using spot instances, it said, oh, I don't happen to have spot instances right now. Let me retry. And then eventually it found some. And then it, was preparing the instances for training. This is where it like mounts the data. And then it brought in the image from the container registry. And lastly, it's starting to produce the output of our internal logic. So this is like things that we now are doing in our custom code. It's hitting our entry point. It's starting to parse the configuration choices. It's able to see that we're running the airline data set in single GPU mode with XGBoost and 3 cross-validation folds. It's parsing in the hyperparameters. In this case, because we're just doing a sanity check, these are the defaults. Otherwise, these hyperparameters would be set by SageMaker when it's running and orchestrating the HPO. It will send every experiment different versions of these. And then as it runs, we pointed it to the airline data set. So in this particular case, I think we pointed it to the 3-year data set. Let me check here. Yes, the 3-year data set. So this should be 36 Parquet files in here, basically one for every month. So you can see these are the files that got mounted that it's reading and ingesting when it's doing this. And so it has an extra one for metadata, so 37 files. And now it's running the single GPU workflow with this data. So it ingested the data and it has 18 million flights with 14 feature columns, of which one is the target. So like 13, I guess, feature columns and one label. And so it finished the ingestion in about 5 seconds. It did the data split very quickly. And then it fit the XGBoost model in about 2.5 seconds. Again, this is probably not the most complex model because this is just 10 trees of depth 5. These are kind of just simple defaults and more of a sanity check than anything. So we shouldn't expect super high accuracy, but nonetheless, this is just making sure everything works. And so everything completed here in the first run. And so it finished essentially one cross-validation fold, and then it did it again for another cross-validation fold, and then one more time for the final cross-validation fold. And then as a result of that, everything took 19 seconds. And this is the performance of the model across those remixes of the training and test data. You can see that it's pretty close to 91.4/5. So it's fairly tight, and you have some confidence in the robustness of this result. Although this number is fairly low, once again, because the number of trees and the depth of the trees is quite low as well. This is more of just a kicking the tires example. But nonetheless, we see that our workflow ran to completion with our choices, and SageMaker was able to get everything done. And in addition to that, we were able to save 70% by turning on spot savings. So with this, we can now have some confidence that our containerized estimator is working well. So we can actually go ahead and do proper HPO. So I'll show you what that looks like here in just a second, and then I'll open it up to you guys for questions. So, we already specified our search ranges. So now it's up to SageMaker to take this estimator that we know works and to spray it around and, run multiple parallel experiments for us with different settings of these parameters. All we have to do that is just tell it, what do you want to be our metric, the thing that we are going to be scoring ourselves on? And so the way that you tell SageMaker this is in the form of a regular expression. And so you're saying, whenever you see the string final score, that's the thing that I want you to parse. And if you attend back to our output, our final score essentially is being produced at the very end. So this is what SageMaker will parse out of our output and use string matching on to understand that the result of this container run with the particular hyperparameter settings that it was given was this result. So that's how you know what to look for. And with this metric definition, you can build on the SageMaker Python API once again. This time, you're not building an estimator, but rather you're passing in the estimator in as an argument to a hyperparameter tuner. So this takes in that estimator we just finished, this metric definition for our final score, and it also takes in the hyperparameter ranges that we defined above, the search strategy that we set to random, the maximum number of jobs to run, and the maximum parallel job. So for our case, this was, I think, 10, and this was 2. So with that, we're almost there. This is just a quick summary of your choices, just so that you can kind of confirm that everything's looking good before you kick off this compute. And then here you actually launch the work. So here you're doing a hpo.fit, and hpo is our SageMaker hyperparameter tuner object. So this will actually kick off potentially a lot of compute depending on how you've set up your experiment. In our case, it will run 10 instances, 2 at a time. And then it will eventually get back to us with the result of those experiments. And so here, this is a blocking call to make sure that we don't get past the cell until this is completed. And once this does complete, we'll be able to see our HPO results, which I don't know if okay, yeah. In this particular case, we can view the results of our runs. So here's our 10 runs. And the best one was 91.54. I think that these guys are, I think the parameter search ranges that we set were a little on the low side, but nonetheless, this is a reasonable result for the 3-year data set. So this is just an example of how we would run end-to-end on SageMaker using RAPIDS. I'll take a quick break here and see how you guys are doing. The other pieces that are in here are, let's see if our notebook is still alive here. I wonder if we should be able to do this also. So the last piece is essentially to take the best model that we were able to find and put ourselves in a place where we can serve this model to the world. So once again, we're going to be leveraging the SageMaker API, and this time we're going to be taking our model and deploying it to one instance, and then we're going to send it input using the real-time predictor API. And in the case of the airline dataset, I already have an example of a flight from 2019 that was 9 minutes early to leave. So this should be a something that the model tells us should arrive on time. There's also an example from 2018 where the flight was 123 minutes late in departing. So this is one that the model should classify as late. So once we take, once this model is done being spun up on an instance, we should be able to ask it queries, and it should be able to tell us, whether or not it thinks a flight is late. And as a sanity check again, we'll ask it about these ones that we know are late or early, just to make sure that the whole process worked. So let me pause there and see how you guys are doing. Is anyone following along? Are there any questions? Maybe we should just take a stretch break anyway. Does this stuff make sense to you guys? Is there is this something that you guys think you might be able to connect to your work? Maybe not in this exact form, but are you getting thoughts about potentially being able to leverage SageMaker stuff? Anyone? Don't be shy. Got a quiet bunch today. Any technical troubles? Is anyone following along? Are you guys able to do this on your side? I'm not hearing anything from you guys, so I'm wondering whether it makes sense to, go into any additional detail here. The next piece I was going to cover is around how you can get a live environment with a RAPIDS kernel in your notebook so that you can actually do interactive development right in the notebook as opposed to just bringing in a workflow that you know is already working. Okay, let's see. So I'm going to be stubborn here and wait for at least one question to come up before moving forward. I kind of want to know if you guys if any of this is making sense, or am I just talking into my own screen? Wow, crickets. All right. I think we can, end it early if you guys are not interested in hearing more. I will wait for just a bit, just in case something comes up, but I don't think it makes sense to do the additional deeper dive if I'm not hearing feedback from you guys on the fact that you're able to follow along, because the next step is going to be a little trickier. So I'll stop here again, give you guys a few minutes, and then if I don't hear anything, I can give you time back.
Hi attendees, if you have any questions to Miro, please post them in the chat or just reply to Miro if he has any questions, please attendees.
Yeah, I'm just curious if folks are not able to access the AWS resources for whatever reason, maybe they don't have an account or they don't have credits or permissions. That's no problem at all. I just don't think that the next piece of the deep dive session makes too much sense. So maybe what I'll do is I'll just show you what it looks like on my machine, and then you guys can see that and have it as a reference, just so you know what's happening under the hood. But I won't ask you to run it because it doesn't seem like folks are really following along on SageMaker from what I can tell. I'll wait for about one more minute to see if any other questions come up, and then I'll show you a little bit more of the inner workings of the workflow. Okay, so let's talk about the sort of the machine learning or the data science that's happening in this behind the scenes workflow that we didn't really dig into very much up until now. So let's see, is this alive? Let me try to clear the kernel. So as we mentioned before, we're working with the airline data set and we're trying to predict flight delays. So the data set, let's go ahead and actually create a local copy of it for ourselves. So we'll download it from the same bucket that we were using in the HPO demo in the cloud. In this particular case, we're using 2 years of data, all the data that's available in 2020 and the data in 2019. I think this actually only goes through July of 2020 because it's like, I think a few months delayed in the public release, but this is fairly fresh data still. So we're gonna go ahead and ingest it into memory. So as I do that, you should see the GPU memory and the GPU utilization jump up a little bit here. Let's see. So yeah, so the memory went up a bit and the utilization went up a bit as I was reading that data. And if we look inside of the data column, we see, you know, all the samples. We can, for example, view them in a vertical orientation. Oh, oops, this is, okay, let's just do it this way. And so we can see things like, you know, the year, the quarter, the month, the day of the week, the reporting airline codes, the origin city, the destination city, the departure time, the departure delay, whether or not it left more than 15 minutes late, whether or not it arrived more than 15 minutes late, how long it was in the air, and the distance covered. So this arrival delay 15, if you remember, is our target variable. So this is the thing that we're trying to predict from all the other features. So again, just because this is kind of a minimal workflow, our ETL step, where you would typically do things like handling missing data, potentially filling in those values using imputation, where you would be trying to, like, you know, predict the right missing value, if you will, based off of the weight of evidence of everything else, or where you might do some additional feature engineering, or if you want to like merge this with other data sources. So you could, for example, get the geolocation of these airports or something else like this. We're skipping all of that and just doing the simplest thing possible. And we're going to be essentially dropping any values or any rows that have missing values. And the majority of these samples end up being canceled flights. So we're okay with that because canceled flights are not really an interesting target for predicting whether or not they're going to be late. They're definitely going to be late if they're canceled. So this is all we do for ETL, is just dropping data. Here's where we split our training and test data. And again, this is what we need to do in order to be able to feed our machine learning models so that we can evaluate their performance. So here is that train test split. And here's our example of our training data. You can see that the indexes are now shuffled from all over the place. They're not just in increasing order. And we have about 700 or 7 million train samples. And so really the only thing left now in our minimal workflow is to go ahead and train our model. And so here we're going to build a more complicated learner than we did with our in the cloud HPO sort of kicking the tires example, where we only had a max depth of like 5 and I think like 10 trees. Instead, we're going to have deep trees or deeper trees with some significant number of them. And then the rest of these parameters, you know, this is a reasonable learning rate. This is a little bit of regularization. And one thing to note is the tree method here is GPU hist, which is how the GPU essentially learns these trees as it builds feature histograms. And so that's what we're telling it to leverage here. So let's go ahead and kick off that training process. You can see the GPU gets utilized. fairly well. This is just one of 4 GPUs in this machine during this training procedure. And then it should, wrap up here in just a few seconds. So it took about 15 seconds to learn these depth 10, 300 of these trees. And now we can go ahead and do prediction with this and see now we're up to 95% accuracy. So this was, significantly better than what we were doing before. We were just using simple architecture. And so we can go ahead and save this model to disk. And we can also point out that we're leveraging the forest inference library, which is a accelerated inference tool that lets you essentially get really great predictions at speed. For folks who are curious, even if you train your model on CPUs, you can still use the forest inference library. And this is, really great optimizations going in here to get the most out of, especially large batch predictions. So that's what's happening under the hood for the single GPU workflow. It's fairly easy, fairly straightforward, very minimal workflow. Really just ingestion, splitting, training, scoring, and then accelerated inference. Since we have just a little bit of time left and there's no questions, I'll also show you what it looks like to run this on multiple GPUs. So let me go ahead and clear this and close it. So the multi-GPU side, I'll show you with CPU and GPU side by side. So let's go ahead and run this so it will restart. We already have this data, so we don't need to reclone it. Here we're creating a local CUDA cluster. So now you might have noticed the memory of 4 of these GPUs went up. And actually, let me go ahead and bring up the task stream and the DAS graph here while we're at it. Let's see. So now we have a cluster of workers instead of just a single worker. And this is all because of Dask. Dask is a really great library for parallelization. I highly encourage you to check it out if you are doing distributed work. And essentially, the code looks very similar to what we did before. So if you look at the single GPU example, let me close the multi-CPU for a moment. Bring this out here. So in the single GPU case, we just did CUDA data frame read parquet with these feature columns, et cetera, et cetera. In the case of the multi-GPU case, we just do Dask cuDF read parquet. So it's very similar API, just Dask cuDF instead of cuDF. And why should I restart this kernel? Okay. And so when I do this Dask cuDF read parquet, it actually returns immediately without doing any of the work. And that's because Dask is sort of doing lazy evaluation. It just builds up a compute graph of the things I've asked it so far. And only when I tell it that I need a result will it actually trigger some compute. So far, it's just sitting in the back and just telling it, like keeping track of all the computations I've asked it to do. So for example, if I ask it for the data after I told it to read this in, it knows that it needs to read something with these columns because I told it to, but it doesn't actually have any values associated with it. Unlike in the single GPU case without Dask, where as soon as we asked it for data, it already had everything populated because this is computed immediately. So in the Dask case, things are lazy. And if we visualize them, we see that there's a compute graph somewhere in the back that's saying, I need to read parquet from all of these files. And I know that I need to do that, but I haven't done it yet. So if you, again, look at the, for example, the shape of this data set, it knows that it has 14 columns, but the actual outcome of the computation hasn't occurred. So it doesn't know how long or how many elements there are in here. We can sort of trigger a computation that forces some compute. And here you can see essentially that there's a task stream to figure out the trigger to figure out how long this was. And so it's telling us that it's about 9 million samples in here. So let's go through and do the same stuff we were doing before. So next we'll drop the samples with missing values. If we visualize what the data is now, it's still just a compute graph that hasn't fully been realized. It's going to be reading data and dropping elements that have missing values. We can chain together more complex computations in here. So like, for example, if we were to do a sum and visualize that, that would actually force all of the the nodes in our graph to link together, because it's going to have to do some kind of aggregation over all of those data chunks. Whereas before, we're just reading them in and then dropping missing values. That is completely independent. All the workers can process that without having to talk to each other. It's not until we do something that requires communication that we bring this graph together. And of course, we can do things that are more complicated, like a mean call, for example, requires a sum and then as well as a count to figure out what to divide by. So these DAS graphs can get arbitrarily complex depending on what you want to do under the scenes or under the covers. For the purposes of what we're doing though, I'm just showing you that Dask is a really powerful tool, and the API looks almost identical to the code that you're writing when you're doing sort of single threaded or single GPU code. But it leverages lots of workers and it figures out how to best place the work on them. So highly encourage you to try it. So here we'll just continue. This is our train test split. So now our train data is, again, hasn't fully been realized, but it knows that it's something that needs to be read in, it needs to have its values, dropped, and then it needs to be split. And then eventually, it's ready to be handed off. Again, none of this has run yet, but here we'll trigger the computation. When we do this persist call, we're actually telling Dask, all of that work that you know about, go ahead and kick it off in the background. And so you should see some of this memory go up here when I run this cell, and you should also see a task graph start to appear where we can actually process this data. So now if we visualize the X train, it sort of took this plot of all the computations it needed to do for each of these, shards of data, and it actually did them. And so it got compressed back down into just a single object of the fully realized version of this data or this computation. So, last but not least, let's go ahead and get ourselves into some machine learning. So here is the model training. Same as before, where the parameters are 10 for depth and 300 for boosting rounds. This time we should be leveraging 4 GPUs when we're doing this training. So let's go ahead and kick this off. And so you should see 4 GPUs being utilized here, which is great to see high utilization counts for complex problems. All right, and let's see the result of that. And again, we're getting about 95% accuracy. So that's a good point for us to sort of stop. Hopefully you've seen what's possible at the highest level, where we can take this workload and just like this notebook, except stripped down. If we just look inside of the workflows, for example, the single GPU workflow, this is almost the equivalent code to the notebook you just saw for the single GPU, except it's now in the form of a .py file. So here's like, the read parquet. Here is read CSV. If you wanted to read in data that way, here's the handling missing data, the drop NA. Here's the train test split. Here's the model training with XGBoost. Here's the model training with random forest. And then prediction and scoring. And so there's one of these versions for single GPU. Here's the version probably most people are familiar with, which is single CPU. So this is pandas and scikit-learn. It should look very similar. So again, pandas read parquet instead of cuda read parquet. Pandas read CSV. Same drop NA call, same train test split, pretty much identical XGBoost and random forest calls. So the single GPU, single CPU code, they should look almost identical with some very small changes. And that's the whole point of RAPIDS, is that you essentially keep developers happy by not changing too much, but just making it go much, much faster. Okay, and so with that, I think I will end the session. Do you guys have any thoughts or questions for me before we wrap? I see that. Can RAPIDS be leveraged to accelerate NLP models like BERT or GPT? Yeah, that's a good question. RAPIDS can definitely be leveraged alongside something like PyTorch to accelerate BERT training. And the role of RAPIDS in that would be to probably accelerate the tokenization, like the string parsing, and then hand off sort of fully numerically embedded representations of the strings to the deep learning framework. So we're actually actively working on use cases where we can show exactly this. RAPIDS is an on-ramp to deep learning NLP models. That's a good question. Awesome. How about, I have a question for you guys. Does anyone here use SageMaker, let's say frequently? Okay, maybe not. So maybe this was a little tricky for that reason. Okay. I think next time, maybe we'll find a way to get free credits for people so that they can come pre-logged in and maybe not be worried about the account setup stage. Is there anything we could have done to make this a smoother experience for you guys? Was the notebook instance spin up a hurdle?
Any questions, audience? Yeah, I think Miro, you can continue. No questions. Please post the questions in Q&A or in the chat.
It took like 5 minutes to come up. Yeah, I think maybe we can start future sessions by having folks come in and just spin up the notebook while I'm talking about slides and stuff. Are you able to make progress in the notebook though once you've started it, or?
Yeah, Miro?
Yeah. Got an error when trying to load the data.
Okay.
Oh, interesting. Can you paste the error, please? It might be your region. Yeah, I see that. Priyashri raised hand. Okay, let's see. Yeah. So it's telling you that you're in a region that is not US East 1 or West 2. So the demo won't run unless you're in those two regions. If you want it to run in a different region, you basically have to copy the data from the S3 bucket that we provide and put it in your region. So yeah, if you're like somewhere else in the world, then you can just switch your AWS region. Again, the way to do that is to, if you navigate to the top, if you go to just AWS console, in the top right, you should see a region selection tool. So you can go to US West 2 or US East 1. And if you're in those regions, when you create your notebook instance, then you should be all set. Oh, you were on East 2. Okay. I'm sorry. I probably should have made that clear when we were starting. My apologies. I have one more question for you guys. Is DAS the only difference between the single and multi-CPU or GPU? So there's multiple workflows. Let's see. There is, I think I understand your question though. But yes, Dask is the only difference between the single and multi flavors of both of the single or the CPU and GPU. So for example, single GPU differs from multi GPU in that only Dask has been added. Yeah, I think if that's your question, yeah, it's a good question. And the answer is yes. It's not super different, with the exception that you have to basically spin up a cluster. You have to do this local CUDA cluster or a local cluster in the case of a CPU Dask instance. But once your cluster is up and running, pretty much everything stays the same, except that like when you're, for example, using your training API, instead of saying xgboost.train, you have to say xgboost.dask.train, and you have to pass in the first argument is your client, which is how you talk to your cluster. But everything else is pretty much the same. So it's very similar API, and you get distributed computation with like minimal change. Great. Glad you guys are finally giving me some feedback. I thought I was just talking to myself here. I have one more question for you guys. Does anyone here do HPO? I'd be really curious to know if this is something that's done by your teams, or is it kind of, I mean, I would argue that if you're a data scientist and you have a model or data set that you care about, you should probably do HPO at least once on it. And if you're someone who's putting things into production, you should probably periodically run it to see if you can find a challenger model to the one that's in production. I'm curious if you guys use HPO, plan to use HPO, are already using, it in production, or is this kind of all over your heads, like, good recommendations, but not really practical? Okay, doesn't sound like we've got too many HPO takers. Well, I hope that you guys can take this and is there a demo notebook which explains how we use RAPIDS for NLP models in PyTorch? Work with data scientist team, but I'm a database, so having them. I see. Okay. Rapids for NLP models in PyTorch. Let me see if I can find something for you. I think there's this thing called Cybert. Let's see. So this is a great blog post talking about how, I think it's primarily focusing on ETL and pre-processing of tabular data. I don't know if this one looks at, oh, it's doing word embeddings. Embedding there, yep. So I think this one is a good one to start with. Let's see. So using Rapids with PyTorch. There's another one, I think Rapids. Let's see. This is another good blog post that uses Rapids to do parsing of logs and then feeding those into an anomaly detection model. Or like a version of B, continue to improve the quality of the Rapids feeding NLP pipelines. So definitely stay tuned. If you just look at the Rapids Medium blog posts, then just keep your eye on this place, and you should see some more really great Rapids NLP content. Awesome. Okay, well, since I know folks were struggling with AWS stuff, I think we'll probably call it here. And next time I'll try to provide maybe a set of detailed instructions that you know, if you're interested in following along, you can try beforehand before coming to the session so that you're pre-spun up. But yeah, thanks so much for your guys' time and attention. I appreciate you staying through to the end. And if you have any thoughts or questions, definitely feel free to reach out either on GitHub or through